last talk of the day is going to be my proposal talking about containing container memory and more CRIU work.
Hello. So, already been talked about CRIU and the container checkpoint restore migration a little bit. In general, CRIU is a tool for checkpointing, restoring, and migrating Linux processes and containers. Now, container is from the bottom point of view, is a collection of seven very different objects, like processes. And each process also have processes have open files, sockets, mount points, etc., etc., etc. And processes are isolated using namespaces, and they also controlled by C groups to ensure resource usage and different things like that. So here's the example of CRIU dump checkpoint, a very simple test application that actually checks if the environment remains correct after the checkpoint and restore operation. And you can see the pages 1.img is the memory dump of that simple application. And the memory dumps are orders of magnitude larger than everything else in the container checkpoint. So I'll talk only about how do we deal with containers memory. So this diagram presents most of the possibilities CRIU can do with the checkpointing and restoring container memory. First of all, it can transfer all the memory from running processes tree into images. Then, either way or another, it reads the images to restore back the processes in memory contents. And it has several additional tools to optimize the whole memory dump and restore to reduce container downtime. So, how Linux lays out a memory virtual address space process, you can check proc PID maps to see what's actually there. So, for example, it was cut from proc self maps and therefore to show the memory map of cut process. Each address space is divided into virtual memory areas, and the virtual memory areas are populated with pages, and some of the addresses are not populated because nobody actually tried to access pages at that address. So when CRIU performs memory dump, first of all, it freezes all the processes it like to checkpoint and injects parasite code into the victims. Most of it is done using ptrace calls with different parameters. And the next step, CRIU parses both PID maps and S maps to determine a virtual address space layout of the processes. And it also detects a relationship between virtual memory areas and the files that back the virtual memory areas. The next step is CRIU engine sends command to parasite in the victims to transfer memory contents to an open pipes, because for now it's the most efficient way to share some memory between different processes without actually copying it. Using ptrace would be way too slow, and there is no other system call that you can use to do the same thing. What happens is just memory becomes mapped in both victim process and the pipe, and then a CRIU engine can map the same memory using the same pipe. And the final step is to transfer the pipe contents into the images on disk using splice system call. When CRIU performs the restore, it actually does all the way around. First of all, it recreates virtual address memory space by pre-mapping the DMAs and then moving them into the correct addresses. And then it reads memory contents from the image files and moves it into, splices it into the appropriate places in the processor's address space. And depending on the CRIU version, some of the mapping and pre-mapping may be done and reading of the data may be done in different stages. The most recent CRIU versions do everything nearly before the point where the processes are resumed and allowed to run. So to implement micro-migration with the CRIU, you just need checkpoint on source, transfer everything from source to destination, and then restore as a destination. This approach has longest downtime possible because the transfer in memory state for an application that, for instance, is 1 GB of memory is quite time consuming. So to optimize this a little bit, one can use what we call page server, so that instead of waiting until the complete memory dump is finished and then transferring the memory image file, you can write all the pages directly to the destination node and save some latency during the migration. Now, the next technique is the iterative memory migration, which is used both by virtual machines and containers. So, at every iteration, we check what is the memories that have been changed between the iterations, and on the transfer delta from the previous round. Hopefully, the process will converge, though it's not completely correct for certain types of applications that have large memory footprint and that have large rate of working set modifications. So when pre-dump is used, restore knows to choose the right image and select the appropriate data from the correct iteration of the dump and fill the process's memory appropriately. And the next optimization is what we call laser restore, which is on-demand paging for the restored processes. We just start processes as they are without filling their memory entirely, well, actually leaving them with empty memory. And then every time when process attempts to access certain memory page, we get page fault notification using user fault FD mechanism, and then we fill the appropriate page from the image file or from the network, depending on the configuration. Currently, we do not have some smart heuristics to ensure that we do address working set changes and we can do some smarter things. We just page was reactive. But we definitely plan on improving in that point. And the last one is actually lazy or post-copy migration. The dumping source doesn't actually dumps any of the memory, it just transfers them from a victim's address space into pipes and keeps them there. And on the restore side, the processes are started without their memory, and all the virtual memory of the processes is registered with user fault FD. Again, as this laser restore, every time a process tries to access a memory page, we get user fault FD notification and request the page from the source node. With that, workload can resume almost instantly. However, the first several milliseconds or seconds, depending on the size of the working set, it will run much slower than it would have been running with all the memory whatsoever. That's
there's like an undefined protocol effectively to transfer the pages, right? From the source to the target of demand. Have you considered looking at RDMA?
Yes, we did. Actually, a colleague of mine exists in the next room is trying to do this, and it still doesn't work. So with RDMA, most probably we'll get latencies much lower.
Yes, yeah.
I have a question about the page server with the lazy migration. How long does it work? I mean, there is a possibility that the new migrated process on the new server will not ask for all the pages initially created on the first server. Is in that case page server pushing those other frames? Okay, maybe I'll explain briefly again. We have the server A and B. We move process from server A to B, and the process running already on server B asks for only a couple of those pages. What happens with the memory on the? What happens with the memory and the page server on server 1 and server A?
Eventually, it will get the server B. So what we're doing now, we prioritize page faults over the rest of the memory, but we still have some background transfer for the memory that is not still requested.
Does that get not fully implemented? Like we could imagine having a bandwidth limit. Right? You could say I'm willing to do that much.
It's still the biggest point of the laser migration. How do we decide what is going on where and when?
Because anything that goes through user page fault, you obviously want that immediately for the background one to create restrict the rate so that you don't go through.
Yeah, but again, and with user fault, we have additional copy, and with user fault, we do all different things that we want to do otherwise. On the other hand, for some workloads, for scope is the only way to migrate.
Other questions? Once, twice. Oh.
Sorry, I don't really know. I don't know CRIU, but a lot other parts of the process that are not memory but file descriptors, etc.
It's all there. Like the part of the process state is detected via different proc interfaces, and part is detected from the parasite code that is injected into the victim. For instance, the file descriptor table, you can have part of it from my proc, and some part of it is not accessible, so you need to be in the same process address space, run code in the same process address space. So file descriptor, socket, activity connections, whatnot. Whatnot is actually real hardware device states. We are not capable of checkpointing and restoring.
And with typos craziness, you should actually be able to even do some of the buffers and stuff afterwards. You could intercept some of the receive message, send message or something, and then refill those as needed. But fully does both things, given that the inside data tends to be pretty minimal.
But generally, for actually a real device, we need to have some support from the kernel to do this.
Anything else? No? Well, thank you. And with that, that's the end of this conference. So thank you very much for attending, and we'll see you next year.